Auroras, the captivating displays of light in the sky, are natural wonders and intricate interactions between the sun and Earth. These luminous phenomena, known as the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere, result from charged particles from the sun colliding with Earth's magnetic field and atmosphere. This magical dance of lights, seen as shimmering curtains or arcs, is a visible manifestation of the dynamic relationship between solar activity and our planet's magnetic shield. The introductory hook of our presentation sets the stage by highlighting not only the beauty, but also the underlying significance of auroras as warnings or messages from the sun. Understanding auroras is crucial as they are direct indicators of space weather, which can have profound effects on technology-dependent societies. For instance, geomagnetic storms, often heralded by intense auroras, can disrupt satellite communications, induce voltage in power lines, causing blackouts, and affect navigation systems. This understanding leads to practical applications, such as predicting and mitigating the adverse effects of solar storms on critical infrastructure. A poignant example of the impact auroras signal is the March 1989 event, when a massive geomagnetic storm caused the collapse of the Quebec power grid in Canada, leaving millions without electricity. Another instance is the ongoing research by space agencies to develop better forecasting models that use auroral activity to predict solar weather patterns, thus safeguarding technologies and essential services that modern society heavily relies on. While the beauty of auroras is undisputed, some challenge the narrative of viewing them solely as ominous warnings. Cultural interpretations, particularly among indigenous communities, often view auroras as spiritual or ancestral carriers, enriching their significance beyond scientific explanations. Moreover, the unpredictability of auroras poses challenges in developing accurate prediction models, an ongoing debate in the field of space weather. Despite differing viewpoints and challenges, auroras indisputably link to broader topics of space weather and its influence on Earth. They emphasize the interconnectedness between celestial phenomena and everyday life, underscoring the importance of understanding and preparing for the sun's volatile behavior. This initial glimpse into the secret life of auroras not only mesmerizes with their beauty, but also serves as a critical reminder of Earth's place in the solar system's dynamic environment, setting the tone for a deeper exploration into these celestial phenomena. An aurora, commonly referred to as the northern lights in the northern hemisphere or the southern lights in the southern hemisphere, is a natural light display characterized by swirling, colorful patterns in the night sky. This phenomenon is caused by charged solar particles colliding with Earth's magnetic field and atmosphere. As these particles from the solar wind approach Earth, they are funneled towards the polar regions by the planet's magnetic field, where they interact with gases such as oxygen and nitrogen. This interaction results in the vibrant energy releases we observe as auroral displays. The significance of auroras extends beyond their captivating visual appeal. They serve as vital indicators of solar activity and space weather. Auroras herald disturbances in the magnetosphere, often caused by solar flares or coronal mass ejections. Understanding these phenomena can help scientists predict geomagnetic storms, which have potential implications for satellite operations, communications, and even power grids on Earth. One real-world application of studying auroras is in protecting satellite technology. Spacecraft and satellites in orbit can be affected by increased solar activity, risking instrument damage or signal disruptions. Monitoring auroras aids in understanding space conditions, allowing for preemptive measures to safeguard these technologies. Another example is their role in scientific research. Auroras provide insight into the complex interactions between solar winds and Earth's magnetosphere, furthering our understanding of planetary magnetic fields and atmospheric behaviors. While many marvel at the beauty of auroras, they do not come without challenges. Some view them purely as tourist attractions, leading to potential disruptions to local ecosystems and light pollution concerns. Moreover, there are ongoing debates in scientific communities regarding the precise mechanisms and variations that cause different auroral features, demonstrating a need for further research and discussion. In the wider context of the topic, auroras are a vivid demonstration of celestial influences on Earth. They connect to themes of space weather and its earthly impacts, emphasizing the interconnectedness of our planet and the universe. At their core, auroras remind us of the dynamic interactions between solar activity and terrestrial environments, stunning displays with significant scientific and cultural relevance. They tie into broader conversations about the importance of space research and preparedness for geomagnetic events, positioning them as both a natural wonder and a critical subject of study. Auroras, dazzling displays of natural light in Earth's polar regions, are one of the most captivating phenomena visible from our planet. Known as the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, these lights are the result of charged particles from the sun interacting with Earth's magnetic field and atmosphere. Solar winds carry these energized particles toward Earth, where they collide with gases like oxygen and nitrogen in the atmosphere, leading to the mesmerizing colors of auroras: greens, reds, pinks, and purples. The significance of auroras extends beyond their beauty. They are a visible manifestation of the dynamic relationship between the Earth and the sun. Auroras signal the sun's constant activity, which has profound implications for our planet's magnetic environment. This interaction is a natural reminder of the sun's powerful influence, where increased solar activity can lead to more intense auroras and sometimes even disrupt satellite operations and communications on Earth. For instance, during solar maximum periods, when solar activity reaches its peak, auroras become more frequent and intense. The northern lights are often visible farther south than usual, providing a spectacle not just for those in high-latitude regions, but also for audiences closer to the equator. Another illustrative example is the impact of solar storms on power grids. When a strong solar storm occurs, it can induce electric currents in Earth's magnetosphere, at times leading to widespread power outages, as happened in March 1989 in Quebec, Canada. Some scientists and space weather researchers argue that studying auroras can help us better understand and predict space weather events, potentially minimizing their adverse impacts on technology-dependent societies. However, there are challenges and controversies associated with understanding auroras. Although we know they are linked to the magnetic and solar activities, predicting exact timings and intensities remains difficult due to the complex nature of space weather. This point about auroras relates to the broader topic of the sun's impact on Earth, shaping our understanding of both immediate climate implications and longer-term technological vulnerabilities. Auroras don't just illuminate the sky with their beauty, they teach us about the underlying forces of nature and their potential influence on human activities and technologies. By exploring auroras in this context, we appreciate not only a stunning natural phenomenon, but also gain insights into the vital balance of forces that shield and sustain life on Earth. The auroras, both borealis and australis, are naturally occurring light displays, predominantly seen in high-latitude regions around the Arctic and Antarctic. They manifest as vibrant, shifting curtains of light in the sky, caused by the interaction between charged particles from the sun and Earth's magnetic field and atmosphere. This captivating phenomenon exemplifies the powerful dynamics between our planet and its celestial neighbor, the sun. The auroras serve as a visual representation of these interactions, highlighting the solar activity's influence on Earth, far beyond mere aesthetic marvel. Understanding auroras' significance lies not only in their beauty, but also in their role as indicators of solar activity. They provide us with tangible examples of space weather, crucial for satellite operations, radio communications, and even power grids. Auroras are, therefore, more than just light shows. They're important scientific phenomena that help us predict and prepare for solar events that could impact our technology-dependent world. Consider the robust streaming of the aurora borealis in Fairbanks, Alaska, where local tourism thrives on winter visitors seeking to witness this spectacle firsthand. Similarly, the aurora australis has become a focal point for astrophotographers and researchers in regions like South Tasmania and the Southern Ocean. These real-world examples illustrate the aurora's value both culturally and economically, as they inspire wonder and drive scientific inquiry. Supporting the idea of auroras as critical space weather indicators, scientists emphasize the importance of monitoring solar activity for the safety and functionality of technology systems. As awe-inspiring as they are, auroras are reminders of the sun's potential to disrupt modern conveniences. However, there are challenges linked to our understanding and communication about auroras. For example, the misconception that auroras can be directly predicted or easily observed from any location remains widespread. Additionally, debates continue around the funding and prioritization of research into such phenomena relative to other scientific endeavors. In the broader context, auroras connect intimately with the topics of solar activity, magnetosphere dynamics, and atmospheric sciences. They enhance our understanding of these interconnected systems, and in doing so, reinforce the urgency of space weather studies and safeguarding global infrastructure. As we delve deeper into the aurora's nocturnal dance, we unravel more about our planet's protective shield and our relationship with the cosmos, urging continued exploration and appreciation of this celestial ballet.